Okay, welcome back. Let's just clean up infinite sequences. And the only thing we have to sequences, there's two theorems. One is called the Squeeze Theorem, and the other is called the Monotonic Sequence Theorem. Now these two aren't really going to come into play for us much at all. However, they're highly, highly theoretical. When and if you take mathematical analysis, you'll be using these quite a bit. Let's just illustrate, let's write down the Squeeze Theorem. All that says is if there's two sequences that converge to the same limit, and you can show there's another one in between, that means that one in between will converge as well. Or said differently, or written down, if sequence A sub n and another sequence, I'll go to C sub n, converge to a limit L, and A sub n is less than, there's something in between them, which is less than C sub n, for that n being sufficiently large, somewhere along the line this is true, then the sequence B sub n converges to L as well. Again, the Squeeze Theorem, where we use that in analysis, we show all kinds of crazy stuff with the Squeeze Theorem, but here we're not going to be using it too much. Just bring it out because it's important and it's in this particular section. Here's how it works. Show that the sine of n over n squared converges. I'm sure that you would look at that and say, oh, I know it converges to 0 because this is oscillating, that's just getting further and further up. But so we know it, but let's just do it using the Squeeze Theorem. And in order to do that, note the range of the sine, the range of the sine is between 1 and -1 inclusive. And so I want to make it look like this. I'm just going to divide everything by n squared. Then and we have something that looks like that. This is the one we're trying to, this is the sequence we're trying to show convergence. And so note the limit, and then goes to infinity of -1 over n squared equals the limit of n, the limit as 1 over n squared equals 0. Therefore, the limit of the sine of n over n squared is equal to 0. The sequence equals 0. By the Squeeze Theorem. That's that. Again, I'm not even going to ask you to do a problem regarding that. It's just out there. It's a very important theorem. Okay, let's do a monotonic sequence theorem. I'm going to erase this and here. Write monotonic sequence theorem here. Whoops, monotonic sequence. There, and erase the rest of the board as quick as I can. Okay, and what we're going to do here, first off, we have to define the word monotonic. I don't think we have that yet. Definition, okay, whoops. Monotonic is either increasing or decreasing. So first off, we're going to define decreasing. A sequence, A sub n, is increasing if A sub 1 less than A sub, increasing, yeah, A sub 2, A sub 3, A sub 4, less than A sub 5, all on down. It's called increasing, and we'll put decreasing here. If we reverse the signs, the smallest one is here. And if that's the case, if so, the sequence is called monotonic. Monotonic. Increasing or decreasing sequences, what we call monotonic. And so here's the monotonic, the monotonic sequence theorem. All it's saying is if a sequence is monotonic, then either a sub n plus 1 is less than a sub n, or a sub n plus 1 is greater than a sub n, depending on whether it's strictly increasing or decreasing. And that's it. That's the theorem, essentially. We're so very close to something called completeness axiom. Of the real numbers, which all of calculus depends on. All of mathematics theoretically depends on the completeness axiom. So just one more example, and then we'll pack that in. Right, one more example, and I'm going to give you a homework assignment and just one problem, and then this one will be over. And the example is show, I don't know what it is. Show n squared over 2 to the n converges. Well, we can do that. In order to do that, what we have to show is that, first off, we need to know if it's increasing or decreasing. I forgot about that. So for 1, it's 1/2. For 2, it's 1. For 3, 9/8. For 4, it's also 1. 5, excuse me. 5, 25, 32s. 6, 36, 64ths. Well, hey, I think we're establishing the fact that it's decreasing. It decreases starting right here. And we're going to show that. To show, we're just going to do an inequality. And all we're saying is, this is decreasing, so we're saying n plus 1. The n plus 1 term, to the n plus 1 has to be strictly less than the nth term. And that's the algebra. Now we're going to find we're going to figure out an n for that algebra, and that'll show it. How about this? N plus 1 squared over 2 to the n plus 1 is strictly less than n squared over 2 to the n. Sorry, I'm standing in front of it. Let's multiply both sides by 2 to the n. Looks like that. How about we multiply both sides by 2? 2, and I'm going to switch the side of the inequality. 2n squared is greater than, and I'm going to multiply this out. 2n. Whoops. Come on. And I'll leave the 1 over here. That's fine. We're not trying to solve this necessarily. All we want to do is find an n. So this will be n squared plus 2n is greater than 1. Or n times n plus 2 is greater than 1. All we want to do is choose an n for that's true. Choose n bigger than 3. Then it's true. Then the sequence decreases from there. And we're saying right here it is. 1, 2, 3. Hey, from here on out, every single one of them is less than the one before. And that's it. Oh, that's it. One homework assignment. I'll get this to you elsewhere, but 456, number 31. I've already made a tape of this solution, by the way. I don't know where it is exactly, the video rather. And so, if you can do that, I'm going to write it down and give it to you in a file. Hey, thanks for listening. See you soon.